Hello, everyone. Let me share the screen. Okay. Please confirm to me that you can see this.
Yes, I can see.
Okay, great. Today we're going to cover a few really interesting topics. But first, why should you listen to me in the first place? So within my 10 plus years long career, I've been working in with a number of tools and technologies. I've been a team lead, returned to the development roles, and worked in a number of both product and as well as outsourced companies. I imagine that many of you may be already working in companies and have practical experience. I actually assume that you know about S.O.L.I.D principles in particular, as you likely studied them in the university, and they're being asked on virtually every interview nowadays. However, for the last 6 to 7 years, I routinely conduct technical interviews myself and being a mentor to junior developers and younger specialists. So what I noticed that while memorizing the definitions, people often do not understand nor the principles themselves, nor the importance of them. And most often they do not use them in practice, actually. So let's give you a little bit of advantage on the labor market. I warn you, I prepared quite a lot of content and going to start from afar. In this tech talk, I will refer a lot the Clean Architecture and Clean Agile books, both authored by the Robert C. Martin, also known as Uncle Bob. You may know him as an author of another popular book, Clean Code. He was also a member of Snowbird meeting, where the Agile Manifesto was originally written, and the one who originally assembled the S.O.L.I.D principles in his paper in year 2000. So I really taken information from the original source. And the foundation of the effective and successful work as a software engineer is a circle of life, something that you can see currently on the screen. It describes the practices and principles of an agile, actually, and even to be more specific, it describes the principles of the extreme programming, which in turn was one of the founding elements of an agile. Thank you, Ken Beck. So this list of practices here is grouped in 4, where the outer circle represents the business practices, middle circle team practices, and the inner circle technical practices. So business practices are essentially Scrum. These practices provide the framework for the way the software development team communicates with the business, and principles by which the business and development team manage the project. It's the most commonly known and accepted and used in practice. Naturally, I will not stop on those much. So I expect that you guys already know about them, all that is to be known. The middle ring of the circle of life represents the team-facing practices. These practices provide a framework and practices by which the development team communicates with and manages itself, like internally. Let's quickly look into them in more detail. And starting with a sustainable piece. So what you see right now in this picture is the first ever expedition to reach the geographic South Pole. It was led by the Norwegian explorer Roald Amundsen. He and 4 others arrived in the pole 14th of December 1911. 5 weeks ahead of the British party led by Robert Scott. So Amundsen and Scott were effectively racing to become the first person to reach the South Pole. The Norwegian explorer have won and safely returned to his base, became explorer superstar of a time. He travels the world with his lectures about the expeditions and actually wrote his name into the history books. Scott and his team, on the other hand, died on the road back from the pole. The two expeditions took a very different approach of making the progress. The Scott, the British dude, he decided to make as much progress as his team could during the good weather periods and hide in tents during the bad weather periods. On the good days, he was pushing his team to the very limits to get as much distance as physically possible. Amundsen made a rule not to move more than 25 kilometers a day, good or bad weather. They were making steady progress every single day. They were sometimes making a little bit less than a target on a bad day weathers, but making progress regardless. On good days, they would stop and break a camp as soon as they reached their target. Even on the last part, as story goes, the weather was good and the distance was about 75 kilometers. If they would push, they could actually make it in a day. Well, they did it in 3 days instead by sticking to the schedule they put on themselves. As a result, when Scott's team reached the pole and found the Norwegian flag and realized they were like 5 weeks late, the team was exhausted, demoralized, and without any will or strength to return to safely to their base. Same goes in the software development. If you're running a project in this kind of death march or crunch style, your team's personal actual performance will diminish with an asymptote. By the time you're reaching the release, if you're reaching the release, you are tired, ineffective, burned out, and not ready to face real users abusing your software you just put into production. So unlike student projects, software is not abandoned and forget on the release day. The release is the very beginning of the product lifecycle. The difference between the software engineer and the mere coder whose work can and will eventually be taken over by the artificial intelligence, the software engineer builds a system that lives in production for decades if needed. So software product development is a marathon, not a sprint. So we developers often buy into a familiar lie. We can clean it up later. We just have to get it to the market first. We have to make it before the deadline to pass the work to a teacher. We have to just give it into in a somehow working condition, and then maybe we can fix it up. Of course, things never do get cleaned up later. The bigger lie the developers buy into is the notion that writing a messy code makes them go fast in the short term and just slows them in the long term. Well, making mess is always slower than staying clean, no matter which time frame you're using. But we're going to get back to this topic shortly. Next, team practice is a collective ownership. It's an important one. So any member of the team can check out and improve on any model in the project at any time. The software development team owns the code collectively. Like collective code ownership, in simple terms, is sharing code and design responsibility among the team members. A sole developer who is working on a piece of model in a non-trivial project should consider letting other team members look into their code and do necessary refactorings. It is inevitable that someone would not be around for a certain reason, either they're sick or has like an important appointment to attend to. When managing an existing system, it is unavoidable to have a defect. With a collective ownership, any programmer can pitch in and apply the fix as soon as possible. In simple words, we want to raise the bus factor as high as possible. Bus factor is, by the way, the number of key developers that need to be hit by a bus to kill a project. So death under the public transport is not the only reason of losing team members. People change job, getting vacations, sick leaves, etc. It also creates a discipline for programmers. Collective code ownership forces programmer to write better code, as he knows that someone is watching him. Always think that the one who will check your code is a psychopath who knows where you live. You have to be more careful when you're writing your code then. Code reviews is one of the practices to implement the collective ownership, but also pair or even mob programming. So many of you were kind of doing this discipline, at least partially, without realizing it. Off top, by the way, decent unit test coverage becomes a tool for you to explore the code base more safely, as you're less likely to break something unintentionally. Consequentially, the collective ownership applies it not only to the code of your team, but to all teams, right? When there are multiple teams involved in the building of the system as well. It is okay for you to make changes into services, code bases, or modules owned by another teams when they are when it is required by your task. Ask them to do a code review. Let them know that you made the change, but God, please do not wait for 3 sprints for them to take your task just because they have other priorities from whatever you have on your plate. Moving to continuous integration. In the early days of an agile, the practice of continuous integration meant that developers checked their codes or source code changes and merge them into the main line every couple of hours. All unit tests and acceptance tests kept passing. No feature branches remained unintegrated. Any changes that should not be active when deployed were dealt with using toggles. In modern days, the term of continuous integration got more merged heavily with the continuous delivery and got more from the CD in this perception. But the process that I've just described still lives through under a different name. I guess you already figured it out. Those are the principles of the trunk-based development. So out of it actually grew the continuous build. So when you have a continuous build, it's very tempting to also deploy it to production or at least to whatever environment is safe enough. Therefore, CI/CD practice was born. But let's focus on the build part here. The continuous build should never break. So Mike Tu, an architect in SOTWorks, addressed this issue in his lecture. He described the calendar they put in a prominent position on the wall in their team room. It was one of these large posters that had like a square for every day of the year, similar to what you can see on the screen right now. In any day where the build failed, even once, they placed a red dot. In any day where the build never failed, they placed a green dot. Just this simple visual was enough to transform a calendar from mostly red dots into a calendar with mostly green dots within a month or two. And again, continuous build should never break. A broken build is a stop the press event. It means sirens going off, big red lights spinning in like CEO office. A broken build is a big effing deal. And the programmer is supposed to stop whatever they are doing and rally around to get the build passing again. The mantra of the team must be build never breaks. So the system is always in a working condition. There have been teams who, under pressure of a deadline, have allowed the continuous build to remain in a failed state. This is a suicidal move. What happens is that everyone gets tired of the continuous barrage of this failure emails that you're receiving from whatever continuous build server you have, like Azure DevOps, Jenkins, anything like whatever CI tool you use. So they remove the failing tests with the promise they'll go back and fix them later. We already talked about later, right? Of course, this causes the continuous build server to start sending successful emails. Everyone relaxes and build is passing, and everyone forgets about the pile of failing tests, and they say aside this fix later part. And so the broken system gets deployed easily. But do not buy into this lie of fixing later. Keep the build green and fix the broken one as soon as possible. We're almost done with this team practices, I promise. So once again, metaphor is a practice that creates a vocabulary and a language that the team and the business use to communicate about the system. In his book, Domain-Driven Design, Eric Evans gave another term for this metaphor. He coined the term ubiquitous language, though it's really hard to pronounce for me, so I prefer metaphor term. So what the team needs is a model of a problem domain, which is described by the vocabulary that everyone agrees on. And I mean everyone: programmers, quality assurance managers, customers, users, everyone. Yeah, this book. The innermost ring of the circle of life represents the technical practices that guide and constrain the programmers to ensure the highest technical quality. Those practices are interconnected, so let's discuss them in more details. The first one is a pairing one. So in Ukraine, we have a proverb: 2 heads are better than one. So it's exactly an example. Pairing is the act of 2 people working together on a single programming problem. The pair may work together on the same workstation, sharing the screen, keyboard, and mouse, or they may work on 2 connected workstations. So as long as they see and manipulate the same code base. I prefer tools that are built into IDE, like Code with Me, a great tool to do the pair programming while working remotely. So in the pairing sessions, programmers adopt different roles quite often. One may be the driver and another the navigator. The driver has a keyboard and a mouse, and the navigator has like a longer view and makes recommendations. Another role option is for one programmer to write test, the other to make it pass and write the test for the first programmer to pass. This is sometimes called ping pong. It's lots of fun. Most often, however, there are no roles at all. The programmers are simply co-equal authors. Yes, especially if you're using the code sharing software. Also, this discipline is backing the collective ownership discipline that we've talked before. After all, pairing is the best way by far to share the knowledge between the team members and prevent knowledge silos from forming. It is the best way to make sure that nobody on the team is indispensable. Pairing also replaces code reviews. So word pair kind of implies that there are just 2 programmers involved in the pairing session. While this is typically true, it's not a rule. This is sometimes called as mob programming, when the whole group work together. It's also really cool for the team building. The test-driven development. Well, that's a rich and complex topic that will require an entire separate talk to cover properly. Accountants, they have a discipline that was invented more than 1,000 years ago. It is called double entry bookkeeping. Every transaction they enter into their books is entered twice. Once as a credit in one set of accounts, and again as a complementary debit in another set of accounts. The accounts eventually flow into a single document, which is called balance sheet, which subtracts the sum of liabilities and equities from the sum of assets. The difference must be zero. If it's not a zero, then an error has been made. It was, well, of course, a gross simplification, but let's keep it short. So personally, I a graduate of economical faculty of Lviv University, and I can relate to this discipline a lot. It was invented as a safety net from data errors. I mean, at the end of the line, you're working with something with a monetary value. Accountants are taught in the early days of the schooling that to enter transactions one at a time and compute the balance sheet as often as possible. Ideally, each time you enter a transaction. This allows accountants to catch errors quickly. They are taught to avoid entering a bunch of transactions between balance checks, since then errors would be hard to find. The practice is so essential to the proper accounting that well, it basically became a law effectively in all parts of the world. Test-driven development is a corresponding practice for programmers. More so, I know personally, as someone with economic background, in many companies, accountant team do not leave the room until the balance sheet of the day is zero, which kind of gets us back to the build never fails situation. Yes, so the remarkable experiment was conducted by a guy called Jason Gorman. For 6 days, he was writing a simple program to convert integers into Roman numerals. He predefined a set of tests to know that the work is done. Each day, the task took him a bit less than 30 minutes to complete. Jason used test-driven development on the first, third, and fifth day. On the other days, he wrote like code without TDD. He just wrote it in one go. Clearly, you can see on the chart that the later days were quicker than the days at the beginning. But check this out. Not only test-driven development days are always quicker than non-TDD, but also slowest of the TDD days is quicker than the quickest of the non-TDD days. So only way to go fast is to go well, right? Making mess, as I told before, will slow you down, no matter the time scale, even in the short term. Refactoring is, well, another one of these topics that requires a separate talk to describe. Fortunately, Martin Fowler has done the super job with his book. It's called literally The Refactoring. The second edition has all the examples in JavaScript, by the way. The first one was very in Java. If you do not have this book yet, you better go and buy it right now. You will also see that this book not only explains the refactoring patterns, but also shows how to pull them off step by step, and of course gives you a lot of training in writing code in test-driven development style. The process of refactoring is described by 3 rules of TDD in what we know as red green refactor cycle. So first we create the test that fails, then we make the test that passes. We make a test to pass, then we clean up the code and return to step 1. And the idea is that you write every time the minimum amount of code to move to the next step. And I mean like very bare minimum. You write a line of code for the tests to pass, like to call your class that does not exist yet. As long as it's enough to make the test fail, you stop with it and move to actually defining the class. You define the class, test started to be green, go return and repeat the operation. The idea here is that writing code that works and writing code that is clean are 2 separate dimensions of the programming. Attempting to control both dimensions at the same time is very difficult at the best. So we create the 2 dimensions into 2 different activities. We separate them into 2 different activities. To say differently, it is hard enough to get code working, let alone getting code to be clean. So first we got to focus on getting the code working by whatever messy means occur to your meager mind. And then once working with the tests passing, we clean up the mess we made. That's the part that people often skip, cleaning up the mess. So it's not fixing up later. This is the continuous process. It's a part of the work that's happening all the time. So this makes it clear that refactoring, is a continuous process. It's not the one that has to be performed on a scheduled basis. Don't make huge mess for days and days and then try to clean it up. Rather, make a very small mess over a period of a minute or 2, then clean it up. That small mess. Remember, we've talked with entering single entry into accounts at a time. That's the same principle here. And finally, the simple design. This practice is one of the goals of refactoring. Simple design is the practice of writing only the code that's required with a structure that keeps it the simplest, smallest, and the most most expressive. The designs of a software system range from quite simple to extraordinarily complex. The more complex the design, the greater the cognitive load placed on the programmers. That cognitive load is called design weight. The greater the weight of this design, the more time and effort it is required for the programmers to understand and manipulate the system. Sometimes it's harder to achieve than say, however, but remember, we are doing software here and we have to make it easy to change. In case it has to be hard to change, it will be called hardware. There are actually widely recognized principles that support the simple design approach called KISS. Oh, not that KISS, this KISS. Keep it simple, stupid. This does not tell us, however, how to achieve the simplicity. S.O.L.I.D does. The S.O.L.I.D principles tell us how to arrange our functions and data structures into classes, and how those classes should be interconnected. The use of the word class does not actually imply that these principles are applicable only to object-oriented software. The class is simply a coupled grouping of functions and data. Every software system has such a grouping, whether they're called classes or not. The S.O.L.I.D principles apply to all of these groupings. Later you will see that what works for several classes or your modules in Node.js that you're exporting, or a bunch of functions that you keep in the same file, or even components that your React application quite often works for arranging microservices and designing large-scale systems. The goal of the principles is the creation of these mid-level software structures, basically, that tolerate change, are easy to understand, and are the basis of the components that can be used in many software systems. So the first letter of S.O.L.I.D is a single responsibility principle. It's an active corollary to the Conway's law, which says that best structure for the software system is heavily influenced by the social structure of the organizations that uses the software system, so that each software model has one and only one reason to change. Of all of the S.O.L.I.D principles, the single responsibility might be the least well understood. That's likely because it has a particularly inappropriate name. It is way too easy for the programmers to hear the name and then assume that, well, that means that every model should do just one thing. Well, make no mistake, there is a principle like this when the function should do one and only one thing. We use this principle when we are refactoring large functions into smaller ones, and this we use it at the smallest, like lowest levels, but it's not one of the S.O.L.I.D principles. S.O.L.I.D principles about the mid-level. It's definitely not the single responsibility principle. So historically, the single responsibility principle has been described this way: a module should have one and only one reason to change. Software systems are changed to satisfy users and stakeholders. Those users and stakeholders, or in a more general word, actors, are reasons to change. That is the principle is talking about. Perhaps the best way to understand this is by looking at the symptoms of how to violate it. So this class employee violates SRP because those three methods that we see here are responsible to three very different actors. The calculate pay method is specified by the accounting department, which reports to Chief Financial Officer. Report hours method is specified and used by the Human Resource Department, which reports to Chief Operation Officer, and save method is specified by the database administrators, which derives from the Chief Technical Officer. By putting this the source code of these three methods in a single employee class, the developers have coupled each of these actors to each other. This coupling can cause actions to be well, the CFO team to affect something that COO team depends on. For example, suppose that calculate pay function and calculate hours function has a common algorithm for calculating non-overtime hours. Suppose also that developers who are careful not to duplicate code because of dry, don't repeat yourself. So those developers put this algorithm into a function, hidden function, a private one called regular hours. Now suppose that, chief financial officers, teams, accountants, they decide they want non-overtime hours to be they want it to be tweaked somehow. In contrast, the COO team in HR does not want this particular tweak because they use non-overtime hours for different purpose. You see the problem here, right? Change was requested by one of the stakeholders, and it affected the output of another who would not know about this update in the first place. Multiple months and wrongly, multiple months can pass before the inconsistent overtime calculations will be detected by someone, and it potentially affected hundreds of people if you're talking about the big organization. Now, imagine that two different stakeholders require changes simultaneously and they are conflicting. So two different developers and two different teams do this change. And at the very least, you will end up with a merge situation. But how to fix it? There are many different solutions to this problem, actually. But each moves the function into different classes. Perhaps the most obvious ways to solve is to separate the data from the functions. The three classes share access to employee data, which is a simple data structure with no methods at all. Each class holds only the source code necessary for a particular function. Three classes are not allowed to know about each other in the first place. Thus, any accidental duplication and merges are avoided. Now, in order to work with a single class instead of three, which is inconvenient, you can use a facade pattern. The employee facade here contains very little code. It is responsible for instantiating and delegating the classes with functions. There are more than one way to achieve the SRP here, by the way, but the principle is same. Scoping the functionality related to the same actor together. The single responsibility principle is about functions and classes, but it repeats in a different form at two more levels. At the level of components, it becomes a common closure principle that we're not going to cover here. At the architectural level, it becomes something called access of change, which is something that's responsible for the creation of the architectural boundaries in the first place. On the other hand, if you put a single model or component or microservice instead of a single class, and how you arrange the related functionality of a multiple services or models of components. Okay, the gist of this software, the gist of software systems to be easy to change, right? So we already mentioned that. Software system must be designed to allow the behavior of those systems to be changed by adding new code rather than changing existing one. In other words, the behavior of the software artifact ought to be extendable without having to modify its artifact. This, of course, is the most fundamental reason that we study the software architecture. Most students of software design recognize open-close principle as one that guides them in the design of classes and modules. But this principle takes on even greater significance when we consider the level of architectural components. Imagine for a moment that we have a system that displays a financial summary on the web page. The data on the page is scrollable and negative numbers are rendered in red. Now imagine that the stakeholders ask that the same information to be turned into a report that will be printed on a black and white printer. The report should be properly paginated with appropriate page headers, page footers, and column labels, and the negative numbers should be surrounded by parentheses. Clearly, some new code must be written, but how much of an old code will have to change? Well, in a good and simple software design, we would reduce the amount of changed code to the bare minimum, ideally 0. How you ask? Well, by properly separating the things that change for different reasons, like single responsibility principle we just talked about, and then organizing the dependencies between those things properly by dependency inversion principles that we will talk about shortly. The essential insight here is that generating the report involves 2 separate responsibilities: the calculation of the reported data and the presentation of the data into a web or a printer-friendly form. Yeah, let's look at this scheme. So, having made this separation, we need to organize the source code dependencies to ensure the changes of one of those responsibilities do not cause changes in another. Also, the new organization should ensure that the behavior can be extended without undue modification. We accomplish this by partitioning the process into classes and separating those classes into components. A component A should be protected from changes in component B. Then component B should depend on component A. Yeah. So we want to protect our controller from changes in the presenters. We want to protect the presenters from changes in the views. We want to protect the interactor from changes in anything. The interactor in this position that best confirms the open-close principle. Changes to the database, which would be, remember, the chief technical officer responsibility, or the controller or the presenter, that could be a responsibility of another actors and so on, or the views that can be marketing or whatever, will have no impact on the interactor. Well, if you know the Django 4 design patterns, you can recognize that what you see here is a version of the MVC pattern here, where the interactor would be called a model. That's purposeless. That's how it should be. The open-close principle is one of the driving forces behind the architecture systems, and the goal is to make the system easy to extend without incurring a high impact of change. The goal is accomplished by partitioning the system into components and arranging those components into dependency hierarchy that protects the higher level components from changes in the lower level components. So the Liskov substitution. In short, this principle says that to build software systems from interchangeable parts, so those parts must adhere to a contract that allows those parts to be substituted one for another. Substituted one for another. Yeah, excuse me. The original definition of this principle is very mathematical, actually, and it makes it hard to understand by the majority of readers. So here we can see the human-readable and concise version of it, that subclasses should be substitutable for the classes from which they were derived. This design, you can see on the slide, confirms the Liskov substitution principle, because the behavior of the billing application does not depend in any way on which of the two subtypes it uses. Both of the subtypes are substitutable for the license type. The canonical example of violation, however, of this principle is a famed square rectangle problem. In this example, square is not a proper subtype of a rectangle because of the height and width of the rectangle is independently mutable. In contrast, the height and width of the square must change together. Since the user believes it is communicating with a rectangle, it would easily get confused. The only way to defend against this kind of LSP violation is to add like mechanism to user, such as if statement or case statement or whatever control flow that detects where the rectangle is in fact a square. The interfaces can be of many forms. We might have the Java style interfaces implemented by several classes. We might have several Ruby classes that share just same method signatures without actually having an interface. Or we might have a set of microservices that all respond to the same REST interface, so a same API structure. So this principle specifically, it forces us to build our hierarchy of entities based not on the entity type, right? The shape, that square is still a rectangle, but based on its interfaces. And a simple violation of substitutability can cause a system design or architecture to be polluted with a significant amount of unnecessary extra mechanism, like these if statements that I mentioned before. Okay, this principle of interface segregation advises software designers to avoid depending on things that they don't use. The whole interface segregation principle derives its name from this particular diagram. So let's assume that we have a user one and he uses only operation one, and user two uses only operation two, and user three covers only operation three. Now imagine that this ops class, it's written in a language like a Java or a C#. So clearly in that case, the source code of user one will be dependent on operation two and operation three, even though it doesn't call them. This dependence means that a change to the source code of OP2 in operations will force user one to be recompiled and redeployed, even though nothing that is cared about was actually changed. So the problem can be resolved by segregating the operations into interfaces. If you use the JavaScript, you may heard of the popular recently concept of tree shaking that allows you to have only the codes that you actually use after the building and therefore significantly reduce the bundle size. It is achieved specifically using this principle of interface segregation. Generally, it's not of an issue if you're using the dynamically typed languages like Python, but it's not about the language specific issues either. If you take a step back and look at the root of motivations of this ISP, you can see a deeper concern working here. In general, it's harmful to depend on modules that contain more than you need. Consider an example, an architect working on a system S. he wants to include a certain framework, F, right, into the system. Now, suppose this authors of the framework have bounded this to particular database. So S depends on F, which depends on D. Now, suppose that this database contains features that F does not use, and therefore AS does not care about. It's often a problem of the full stack frameworks that give you everything out of the box, regardless if you need it or not. The lesson here is depending on something that carries the baggage you do not need can cause you troubles that you do not expect. And when we're talking about dependency inversion, the code that implements the high level policy should not depend on the code that implements low level details. Rather, details should depend on policies. Clearly, treating this idea as a rule is unrealistic because software system must depend on many concrete facilities. For example, the string class in Java is very concrete, and it would be unrealistic to try to force it to be abstract. The source code dependency on the concrete Java lang string cannot and should not be avoided. The same goes for Windows local storage in a browser, the JavaScript API. It's very concrete. However, we tolerate those we tolerate those concrete dependencies because we know that we can rely on them, not to change. In this violate concrete elements of our system, it's a volatile concrete elements that we want to avoid depending on. Those are the modules that we are actively developing, and those that undergo frequent changes. Every change of an abstract interface corresponds to a change to a concrete implementation. Conversely, the change to concrete implementation do not always or even usually require changes in the interfaces that they implement. Therefore, interfaces are less volatile than implementations. Once again, it's not about or only about the classes and modules. It can be interfaces between groups of microservices or third-party integrations. You may need to fetch data from external API and implement the fetching directly in the place that requires it, or wrap this into an abstraction with a stable interface. Then, if this third-party API is changed or need to be swapped for another one, you change the implementation or create new implementation without updating the interface, and nothing depends on the implementation details. Another example is unit testing. You mock the dependencies of the test with your stub, and you keep the interface. You know, the Liskov substitution principle, where interfaces are substitutable. And well, by keeping the interface, you're good to go and achieve that 100% test coverage. Yes, so that would be it. Questions? Maybe.
I suppose we will wait if they ask questions in Slack. So maybe you can write your questions in Slack. And if you can check Slack.
Anastasia, will you be able to read those questions aloud? Because I do not have access on Slack on this machine.
We don't have any questions right now.
Okay.
Maybe we will wait.
Okay, it took a little bit more time than I expected. It was almost an hour. I know you guys are very exhausted by consuming this amount of content. I will try to go into Slack from another device. And if you have questions, you can post them. I will answer them in a written form. Yeah.
I don't see any questions. Oh, I know. I see someone typing. You can see Slack?
No, unfortunately, I'm not allowed to have Slack on this machine.
I'll read it for you, okay? So how can proper documentation and communication regarding S.O.L.I.D principles and other development practice be ensured among developers from different teams?
So these practices are universal, right? So as long as all the teams are educated about them and know how to use them, well, you don't have to document this. Then as long as you put as a standard that you're doing this stuff in this way. More so, actually, when you're using the S.O.L.I.D principles, and let's say you have to do something in another team's services, right? A level or module, let's say there are different teams responsible for different modules. And you're opening the code base you never saw before. It actually makes it easier to understand the code base, even if you do not have any documentation about it. That's something that we've talked about, but we're using the principles to have a simpler design to reduce the design weight. You will find familiar patterns. You will find that it's much harder to make a mistake as long as you're following all of this. And most importantly, you will find that it's easier to make change even if you do not know the code base and so on, because you're making additional features or requests by extending functionality, and the functionality is covered by the tests. That, like, the existing functionality is covered by the tests, like the unit tests, because the test-driven development that we all should use. You write a new functionality again with the tests. You have a green build every time. You're free to do the refactoring, and when the new functionality is added and all structures do not work anymore for this, you're free and actually have to do the refactoring to build this new structure that fits more, even without any sort of documentation. It is like more understandable, and yeah, keep the build green, work in small iterations, and you can almost completely skip it, except the important parts like the business requirements and so on. But it will allow actually the easier interaction between teams. I hope I did manage to answer the question. Is there anything else?
I don't see any other questions. Oh no, I see another one. What resources or references do you recommend for further studying S.O.L.I.D and other software development practices?
Okay, so sure. At the beginning, I already in this presentation, I mentioned several books. A few of them at the very beginning. Here, the clean architecture is the fundamental one, where the author of the S.O.L.I.D practices describes them in details, in much more details than I described it. Here, I just try to, he give you distilled version of it. Actually, in this book, Clean Architecture, he goes further and goes how to extend the very same S.O.L.I.D principles on higher levels of the architecture. As I told, the S.O.L.I.D principles, they are about the middle level, right? Also, a great recommendation. Here we have this book, Domain-Driven Design. Yeah, like it kind of supplements stuff, especially if you're going to the higher level. And obviously, this book, Refactoring. I guess in the we'll send the follow-up, and I will add all of the book recommendations in the follow-up or a description. Yeah.
Maybe if someone have other questions, you can write them, because I don't see anyone typing.
Okay, if there are no more questions, let's wrap it up then. Thank you for inviting me to your event, and hope it was fun for you to listen.
Thank you for this amazing lecture. It was nice to hear you, and I hope you have a great day. Thank you. And to other participants, I remind that we have a lunch break, so have a nice rest. See you after 1 hour break. Thank you.
First.